Diese Konferenz wird nun aufgezeichnet.
Hello, everybody. It's my pleasure to present a talk on the importance of realistic gas atmosphere assumptions for combustion classification calculations in FactSage. Now, I will cover
Diese Konferenz wird nun aufgezeichnet.
Hello, everybody. It's my pleasure to talk about the assumption of realistic gas atmospheres for combustion classification calculations in FactSage using Equilib. It's a pleasure to have all of you here, and I will start with a short motivation of this talk. And then I will introduce an unintentional experiment, which I really didn't want to do, but I did it, and I think that if you model it, you learn a lot about what you actually need to do when you want to describe the gas atmosphere. All right, and then I will cover 3 applications of FactSage. I will talk about ash fusion experiments. I will talk about melting and oxidation of sulfides from coal ashes, and I will talk about condensation of salts during cooling of syngas. Okay, what's the motivation? Well, so the typical coal or biomass specification that you find in literature and that you as our customers, of course, measure yourself, are including a variety of different analysis techniques to determine the caloric value, the approximate analysis, the ultimate analysis, the ash analysis, the ash XRD, ash fusion test, and so on and so forth. Now, each test is performed under different conditions with respect to the temperature and the gas atmosphere. So, for example, for an ash analysis, quite often you use a high temperature ash that you produce from the coal, and then you fuse this ash. Now, this means that this ash is not the same as the ash that you have that is going into a coal boiler or a gasification equipment. Now, this is a typical example of such an analysis from this Vasilev paper in fuel that covers, I think, 40 different coals, and then you have there approximate analysis, you have the ultimate analysis, you have the high temperature ash analysis, and the ash fusion test, as well as an XRD analysis of what phases are there in the original coal. Now, in the last year, we have received a couple of questions from customers, and that was actually the real motivation for us to give this presentation. Questions like, what atmosphere should I set to compare an ash fusion test with a FactSage calculation? Or how do I consider slow reactions in the boiler? So because part of your ash particles will not immediately react with the other particles that are next to it. And the question was, how do you consider such slow reactions? Or how do you model the atmosphere when you want to calculate the formation of deposits? Okay, now I want to introduce the accidental experiment I did, which involved the glass of water and my laptop. You can probably imagine what has happened. So I had a problem, right? I had water on my laptop and I want to get rid of it. Now, I thought I should probably take an hairdryer, and I did it. And I was basically blowing the water out. And I thought, well, actually, what do I learn from this? So you find here with the hairdryer, you find the specification of 79 cubic meter per hour airflow. Now that corresponds to 1,320 liters per minute, or 54 moles of nitrogen, where in this assumption I have included nitrogen and oxygen together because we don't expect actually chemical reactions to take place. So 54 moles of nitrogen per minute is what that small thing can blow. But now you have to consider that your keyboard is not open at all places, right? So there, if the air hits exactly on a key, it will be reflected. And only that part of the airstream that hits between the keys will be able to actually contribute to the drying of water that is inside the laptop. Okay, so I estimated an efficiency of 1.8%. So that would be the area fraction that is open to the hairdryer. And that means that we have a flow or an air flow of 1 mole of nitrogen per minute. I assume that I have spilled 18 grams of water, and then this is the accurate calculation that I did. So I set pure liquid, pure gases, and then I blow for 1 to 60 minutes at room temperature, and I can see that in this assumption, it takes me 30 minutes to dry the whole laptop. Now, a colleague of mine told me, well, maybe you shouldn't do it because the hairdryer will have a little bit heated air, so maybe 45 degrees. And that air will take up water, and it will move with the water to other parts of the main board, and there it might deposit the water again, because they are at 25 degrees C. And I thought, well, okay, so how do I model this? Well, it's a rather simple experiment. 80 grams of water plus some amount of nitrogen that is blown, so that I think corresponds to 10 minutes. And then I can see how much water I can take up in the gas phase. Now, you can see that with decreasing temperature, the amount of water that you can transport is obviously decreasing. So this is the difference from here to here would be the difference that we deposit from the warmer parts of the laptop to the colder parts. I was actually, for the fun of it, arranging a simulation model of my laptop drying process. So we have, in the beginning, we have the input air. There is a mass splitter with efficiency of 1.8% that is splitting the gas stream into the reflected gas and the useful gas. Then we have our hot part of the laptop, so the part that I directly blow on, which is maybe at 45 degrees C. There we have our water that is entering, and then we have a phase splitter again. The condensed phase stays in the laptop, and the humid air will then be transported to the cold part of the laptop. And there again, there's some air leaving with some humidity, and there will be some water deposited in there. Now, essentially, these two, or this flow sheet contains two very important scenarios that you need to look out for if you want to set realistic gas phase assumptions. Now, the first scenario is one where you have only part of an input stream that is actually actively participating in the reaction. So that is basically this part. And then the second one is the one where you have reactions taking place at different temperatures, and that also results in that determines what reactions actually take place. Okay, let's start with the first experiment, so the first real application, the ash fusion experiment. So I was considering here a high sulfur containing and high ash coal, which has a softening point of 1290 degrees C. So this is this Balkan coal sample from the Vasilev paper. So in the first approach, I only insert the high temperature ash analysis, which is given here, and I fixed the oxygen partial pressure. So this is rather easily done, and then I calculate at temperatures 800 to 1500 degrees C the melting behavior of the ash. What you see here is that the slag phase starts to form around 950 degrees C. At 1000 degrees C or a little bit above that, you start to form a gas phase. And all the other solid phases must not really bother us right now. Is this realistic? Well, if you look into the gas phase, this is the activity of the gas phase species, and you can see that the oxygen partial pressure is, because we have set it like that, always fixed at 0.21 atmospheres. However, we have an SO2 partial pressure, which is close to 0.8 atmospheres, and that is obviously too high. And our SO3 partial pressure is also rather high, with here around 50 millibars. So the approach I prefer and I suggest is to add oxygen and nitrogen, actually a rather significant amount of oxygen and nitrogen. So here I have inserted 2.1 mole of oxygen and 7.9 mole of nitrogen. The amount of oxygen and nitrogen that I used was set in such a way that it is that the sulfur content is actually much smaller than the oxygen content we have in the gas phase here. Okay, in this case, we have only solid phases up to 1000 degrees C. There we have the initial melting of the first phases. And actually, we don't see the gas phase at all in this diagram because we have in total 10 moles of oxygen and nitrogen as input. So therefore, the amount of gas phases is way above this y-axis scale. But if we look into the partial pressures in the gas phase, we have the nitrogen partial pressure, which is basically constant around 0.8 atmospheres. The oxygen partial pressure is constant at 0.21 atmospheres. And we have rather small SO3 and SO2 partial pressures, which are actually not really visible on this scale. And this is exactly the right condition that you will have in an ash fusion experiment. Now we can see that this has already shifted the onset temperature for the melting by 50 degrees C. And actually even better agreement. So for as a reminder, the fusion, the softening temperature was around 1200 degrees C, and that is most probably because of minerals not reacting because of reaction kinetics. Okay, but at least in this way we have fixed the sulfur partial pressure and the gas atmosphere in a sensible manner. And actually, we could do it with this approach as well. So if we go back to our laptop drying flow sheet, then this is the blue part is the part that we need to consider in this case. So we need to separate the volatile from the condensed species. So we could do a first equilibrium calculation at some temperature, and from that we would take the volatile fraction that would be basically the SO3, because all the rest from the ash analysis will stay in the condensed phases. So that will go towards the gas phase and will leave the system, and then we can fix the partial pressure for the rest of the species and calculate the equilibrium as a function of temperature. So this is very close to approach number one, but with the only difference that we here omit the SO3, because we have seen in approach number two that SO3 is actually all in the gas phase and not really taking part in the melting of the condensed phases. Okay, this is the comparison. This is now approach number three on the left-hand side, and we have the second approach on the right-hand side. And actually above 850 degrees C, there is no difference in the result. So you can perform the calculation in either way, either by fixing the partial pressure of oxygen and removing the SO3. So this is your engineering knowledge that comes into play here. Or you just add a sensible amount of oxygen and nitrogen, and then you will get automatically the right result. Okay, so the two final examples will be a little bit shorter. So the melting of sulfides. So if you have a coal boiler, you add the coal and air at lower parts of this boiler, and then above that you have additional air. So this means that the first part of our laptop drying flow sheet can happen. Because particles might fall based down in here, ash particles and also coal particles, and there they would not have enough air that is there to react with these particles. So we basically have a separation or an amount splitter on the air, where the additional air would move up here not really takes part in the reaction. And at the lower part, we would expect that we have a lambda which is smaller than 1, and yeah, so this is the part where actually sulfur can be important for the melting of the coal edges. So how do we set up these calculations? This is again the same ash analysis we had before. I have still set the SO3 content to 0 because now because now in these 11 to 13 we have additional sulfur from the proximate analysis. Now I have fixed the lambda value by basically varying the amount of air that is entering the system, and then looking at the CO to CO2 ratio, and then I've arbitrarily chosen an amount of air that results in a rather high CO content in the gas stream. And now we can use this fixed alpha value. We can vary the temperature, and we can include the FES liquid in the modeling. And there we see that the FES will actually start melting around 700 degrees C. That is, of course, a problem for the formation of deposits. Okay, and actually, another question that I asked myself was, do we actually reach 800 degrees C? We have such a small alpha value. Yes, so this is the calculation of the heat output when we start with 25 degrees C inlet gas and ashes and coal. And then we see that we always have a negative delta H over the whole temperature range. So yes, with these with this smaller lambda value, you can get up to temperatures like 700 to 800 degrees C easy. Okay, final example, also very short, is the condensation of salts during the cooling of syngas. Now here I've used hazelnut shells from steam gasification in a steam gasification application because this beautiful Phyllis database told me that this is a very interesting ash with high potassium content, high magnesium, 6% magnesium, calcium, but also actually quite a lot of fluorine, phosphates, and so on and so forth. Okay, so we just insert this into Ekphilip, and then we add a steam gasification atmosphere, which I took from this paper by Rauch et al. And that is, so these are the other reactants. Just a short note on the database selection. I recommend here not using FT salt, even though we know that we will have deposition of salt mixtures. The calculation time will be much higher, and probably the result will not be that much different. For very accurate calculations, you can, of course, include FT salt. Okay, and then I did one calculation at 800 degrees C. I saved the gas phase as a stream file, which I then load again in Ekphilip, and then I do a simple calculation where I decrease temperature from 800 degrees C to 100 degrees C, and I look at the condensed phases. So you can see that immediately you have the precipitation of potassium chloride, but also then slightly higher undercooling zinc oxide, zinc sulfide. Sulfite will form potassium carbonate, and there are a couple of other phases with small amounts as well. A better approach is actually, and I would just want to highlight this, to use a shy cooling from gas phase, which requires basically a very short macro processing. Okay, so this was actually also one application where we have this this change in temperature from the process model that I introduced earlier from the laptop drive. All right, so I think I hope I was able to show you that this unintentional experiment and the thermodynamic analysis of it is actually helpful to set realistic gas atmosphere conditions for coal combustion and also for biomass combustion gasification applications. All right, and now I look forward to your questions.